Bueno, vamos a presentar ahora al siguiente expositor, que es Gerhard Harer, quien es nacido en Austria, graduado en Ingeniería Civil y realizado además estudios en Geología Técnica, asignaturas operativas de Mineralogía, Petrología y Geología de Materias Primas en la Universidad de Graz y en la Universidad Técnica de Graz, con una amplia gama de capacitación operativa y educación adicional sobre temas legales, comerciales, de operaciones ferroviarias y relacionadas con la seguridad. El ingeniero Gerhard Harer tomará el tema Posibilidades y limitaciones de las investigaciones geológico-geotécnicas modernas a través de ejemplos de túneles largos de baja altura. Ya lo tenemos conectado, lo escuchamos entonces, ingeniero.
Muy buenos días, saludos de Austria. Por el momento estoy en Viena, lamentablemente no en Buenos Aires. Y si es bien para ustedes, voy a cambiar en inglés porque mi español no es tan bien. Y voy a mirar para la presentación. Sí, un momentito. ¿Es bien para ustedes? Gracias. Sí. I will start a little bit unconventionally because of a history of a friend of mine. He got cancer, and he said he reported me from the hospital that one of his doctors said to him, "Okay, you are less than 1% of cases that we are not able to detect your disease." So anybody knows from us that our doctors, our medicine is highly developed, and since in this business there are cases which are not possible to detect. Similar is in case of site investigation, of geological engineering, geological investigation. So we have very good tools, we have very good processes, but still we also must consider that there are some cases which we are not able to detect. For this, I will give you some examples. We make a short journey, let me say, almost all over the world, of course, with the main focus to some large tunnel projects in Europe. We will go to our neighbors in Austria, to Slovenia, the so-called Divača-Koper railway tunnels, the new approach to the harbor of Koper in Slovenia and the Mediterranean Sea. There is a combined length of tunnel of more than 20 kilometers. We will have a look to the border between Germany and the Czech Republic, to the so-called Erzgebirge tunnel or mountain tunnel, which is under design with a length between 27 and 30 kilometers. It's still under decision. Now we will have a look to my former project, to the Coarm railway tunnel with a length of almost 33 kilometers, which is in the commissioning phase and will go into operation in 1 year. Also, we will have a look back to the colleagues in Switzerland, to the Lötschberg tunnel, was a big tunnel with almost 35 kilometers in length. And at least I found one nice example also from your continent, from the colleagues in Colombia, from the Túnel de la Línea, with almost 9 kilometers in length. So with this, I will give you some examples what I meant. So what is the importance of investigation in this project, of the development of the projects, and what is the role for us of engineering geologists or geotechnical engineers? So we have the responsibility to assess the ground conditions and that's very essential, to provide material properties representing the conditions as natural as possible. Of course, all these projects are fraught with some uncertainties, with some unsteadinesses. So you all know examples. It's because of political reasons. It's because of problems in design, different interpretation of facts, unsteadiness in financing, and so on and so on, which can cause interruptions, which can cause delays, which extend the project, the process of the development of the project, which also lead to changes in the project. And usually also we have to consider that the larger the projects became, which of course normally is the case with huge base tunnels, the greater also the uncertainties became. So this, we as geologists, engineering geologists, geotechnical engineers, this we have to deal with our approach to proper site investigation. Another very important aspect is the consideration of risk. So, of course, most of the people do not like to take significant risks. That's quite clear. So we try to minimize them, or at least to find some solutions to mitigate the risks. What we can see is that, of course, appropriate site-specific, project-specific investigation and characterization can increase the technical reliability and thus can reduce risks. In most cases, also the early identification of these issues allows us to decide to carry out mitigation measures. In the earlier we talk about these measures, the less is their influence to the program and to the budget of the project. And consequently, the potential risks, they can be mitigated, they have to be mitigated. And of course, if we mitigate the risk, of course, this greatly increases the likelihood of our project success. What is the basis? And that's really my deep personal opinion. The basis for any proper site investigation is the development of an engineering geological model. Of course, in early phases, very coarse, very raw, and then step by step getting finer, having more results, having more data. But anyway, we should form, we have to form an engineering geological model, and all our investigation data shall be merged in this model. And this model, of course, shall include all project relevant properties. So not all properties, but all project relevant properties of the soil and the rock and the groundwater. Of course, the micro and the macro structure, the dimension and the orientation of stresses, in particular in case of deep-lying tunnels, and their distribution, the distribution of these properties in the project-relevant environment. If we have a geological and engineering geological model, so this enables us to have a three-dimensional understanding, which is important in particular in case if we talk about complex situations. And by having this, also these models allow us to communicate to other shareholders of the project these complex informations. So what I said before, these models are not static. They must be continuously evaluated and updated throughout the course of the entire course of the project, which starts from the early phases of design and to the end of construction. And in the future, with the technologies of building information modeling and also artificial intelligence, I think this will give us another good tool also for updating and for working much better than nowadays with these engineering geological models. Which are the elements of engineering geological investigation? So of course, this is collecting all the data, all the available data, and at least from my personal experience, all over the world, data is available. Meanwhile, also very easy to gather by internet sources and so on, digital way. So it's much easier than some 20 or 30 years ago. We have all these techniques of data collection by means of remote sensing methods. We should not forget to engineering geological mapping. I will talk a bit later about this, about all these possibilities which is provided from sounding and drilling in combination with geophysical survey, also in combination with in situ testing and wireline logging, and of course also the testing of our samples in the laboratory. So our advantage is we have a comprehensively filled toolbox. So this is available for us, and these tools shall be used for site investigation. So, but of course, which kind of tool we use is highly influenced from different facts. For instance, the project requirements, the phase of the project. Is it a very early stage of the project? Is it in a later phase? About the complexity of the geological, hydrogeological, or geotechnical environment, size and shape of the project, legal conditions, political conditions, climate reasons. For instance, in the mountains, you cannot do field mapping during winter days. So like the picture is shown here, drilling works are not that easy in winter days compared with warmer periods, and so on and so on. So that there are a lot of aspects which shall be considered, which can influence our investigation, which can influence our decision of tools. But finally, all these negative effects, they should never be used as a reason not for striving the highest possible quality and not pursuing a coherent approach. This is our responsibility as engineering geologists and geotechnical engineers. But what we need for this is time, we need resources, and we need budgets. And all these must be seamlessly integrated in a structured project development process. And we, as the geologists, as the engineers, we have to fight to gain this. So it's our responsibility. Let me have a look to a typical structured investigation project. So we know it's influenced from the project phase, from the requirements, from the strategy. It can look like this. So here you see in the middle the ongoing project phases. And for instance, you start in the very early phases with all this office data collection, probably compared with first data from field investigation, from geological investigation, also considering some data, first data of sampling, of testing, of hydrogeological measurement, and then you form a preliminary geological or engineering geological model. And this model, only on this basis you should go to make the first steps for subsurface investigation. So you should not drill, you should not do any subsurface investigation without having at least a general idea about the three-dimensional conditions of your ground to be investigated. And of course, by making this subsurface investigation, you get more information and you see, is your geological model, is it constant or is it reliable and not? If not, so okay, you have to go again for this loop, you have to reconsider this. And of course, this also can be in several loops going on project phase to project phase from course to fine. And I will give you some examples about this. One example is from my former projects from the Gorm Tunnel in Austria. So we had pretty good success due to a structured investigation process. I give you some more data of the Gorm Tunnel. So it is a almost 33 kilometer long base tunnel in the south of Austria. So at the portal sections, we have neogene, geologically young sediments, and in the bases where you see on the right upper picture, we have very nicely crystalline rock mass, but cut with huge fault zones and also covered with deep reaching weathering cover. The overburden reached up to almost 1,200 meters, and we started with investigation, with first steps of investigation, data collection, aerial picture, and so on in 1998. And the opening of the project will be in 2025. So we are talking about a period of 25 or more years. And if you do not have all over this period a structured approach to your investigation, so you will lose a lot of data. You will not find really this red line. So this structure of an investigation for this long-term project is really important and mandatory. So the site investigation for the Gorm Tunnel composed, as I said, of satellite and aerial data interpretation, of course, also gathering all the office data. We mapped in total around 300 square kilometers in an engineering geological way. Over all the phases, we carried out 133 core drillings with maximum depths of 1,100 meters, overall 21,000 running meters. We did mapping and observation of around 4,000 springs, wells, around 10 to 15% of them were continuously monitored over the years. We connected the drillings with geophysical surveys from surface. We did wireline logging. We made in situ stress methods. And because of this specific situation with these young sediments at the portals, we also carried out a system of investigation or exploratory tunnels from both portals. Carried out over a period of, during construction, let it be some 15 to almost 20 years, but the project phase was more than 25 years. You see it here in the same scheme. So you see the ongoing phases of the project phases in the left column. And here you see at the beginning huge intensity of data collection, aerial of all these remote data measurements, and then more and more intensity in engineering geological mapping, forming a geological model, checking this and detailing this with drilling and geophysical survey, and then in some cases additionally from coarse to fine. So like this way, so starting from very rough approach in early phases to in a stepwise detailed process, the more advanced the project is. So this structured investigation process, as I said at the beginning, was carried out with big success, always with the target from cost to fine. And gained us really good success for this project. One aspect which from time to time I think see some deficits in the approach is the performance of engineering geological mapping. From my point of view, it's very important, and I do not know why it's not carried out generally in a really proper way. So, but what we should consider is that, of course, what to show on an engineering geological map depends, of course, largely on the project-specific requirements. So it differs a bit from this, let me say, from this academic, from this pure geological way of mapping. I called it from this conventional geological map. What we should find are really also during this mapping aspects which really have importance in case or for our project. From my point of view, engineering geological mapping is very economic. It costs not much. It provides, in particular in early stages, a large gain of knowledge, but of course, it requires a profound engineering and geological field experience. So you must know, you should work with really experienced consultants. But if you have these resources, really at the end, you will win by this approach. Let us look from Buenos Aires a bit to the north to Colombia. I had the possibility also to join the Túnel de la Línea project. Probably most of you know this. It was with the first tube, the longest tunnel in Latin America, with almost 9 kilometers in length. The tunnel portals are in an altitude of roughly 2,400 meters above sea level, with an overburden of up to 900 meters. And the tunnel crosses the Cordillera Central. And the question was, in parallel to the first tube, to construct a second tube for this motorway between Ibagué and Armenia. The history of this project was not pretty successful, to be honest. For the project, for the second tube, several drillings were carried out by several also international consultants based on this drilling. And you must consider the first tube was already existing. So there should have been mapping data from the first tube, but anyway, additional programs were carried out. In parallel, it was decided in 2004 to drill an exploratory tunnel parallel to the tube. The construction works for the second tube started in 2000, ended in 2008. With the findings of this, the client decided to start with the second tube in 2008, which was expected to be finished in 2016. During the excavation of the second tunnel, the findings did not meet the expectations. There were different fault zones, high water inflow deformations, which also the guys on site could not explain why the situation is different to the expectations. Finally, after 14 years of work and with 500% of increase of costs, 500%, which means 5 times more, the second tube went into operation. you see, based on these data and also based on the data from not existing data from the first tube and not real sound phase mapping data, a longitudinal section was developed. You see, some 2 years later, same profile, same tunnel, the geological conditions looked pretty different. Also, sometimes later looked pretty different. 5, 6 years later, it was simplified, but also a completely different picture, and so on and so on. So also having these data from the pilot tunnel, having the data from the first tunnel, it was not possible for the colleagues really to prepare a sound and a reliable longitudinal profile for this tunnel. So what we found out, that all these considerations were based on one surface mapping, which was carried out some 15 or 20 years ahead. And we decided to go out, and we made, within a few weeks, we made a rough mapping. And you see also from this picture, so the tectonic, the kinematic conditions from the existing idea and from our idea look completely different. And by having this data from surface in combination with the data from the pilot tunnel, so here it's shown a bit better on the plan. So on the first, I showed you our mapping data. So it was possible really to develop a reliable longitudinal section. Then based on this also the construction finally the construction of the tunnel could be finished on this reliable data. So that means without having a sound geological idea also on surface, all these drillings and even not the data from an investigation tunnel help you really to form a realistic picture of your geological conditions. What we should not forget and what we have to look for is really if we apply subsurface investigation, we have to ask for state-of-the-art techniques and for high quality. Here are some pictures again from the Quorum tunnel. I also told you in total we carried out around 21,000 running meters of core drillings with really impressive quality, with a core loss less than 5%, less than 3%. We continuously drilled with drilling diameters larger than 100 millimeters, core diameter larger than 100 millimeters, even in depths to 1,100, 1,200 meters. The orientation of the drilling was no question, so we drilled in each and every direction, vertically, horizontal, upwards, deviated. So all these techniques are available and are no limits. And of course, most of the boreholes were then linked with geophysical profiles. And of course, in almost all the boreholes, we made some observation wells. We did geophysical sounding, wireline logging, and so on and so on. So that means also our drill holes were used in a multi-purpose way. So with this approach, we had really good success for this Quorum tunnel. So to sum up, exploratory drilling campaigns must be properly planned, must be based on a geological engineering model with a clear investigation target for each drilling, and the execution similar to engineering site investigation must be carried out is a task of professionals. I give you a very actual, very nice example now from Divača Koper in Slovenia. They have very difficult situations crossing a karstic environment. So it is a series of tunnels going here to the harbor of Koper with around 20 or more than 20 kilometers of tunnel length in total, heavily castified, and of course it's risky. And so the colleagues there developed a very nice approach to of risk mitigation, of risk reduction in these conditions where karstic features are not really and not regularly be possible to predict it. So their first phase is to drill ahead of the tunnel, ahead of the excavation, really to see, is there a karstic feature, is there a cavity which can be dangerous for the air, which can be dangerous or risky for the excavation. If then they overcome this part, then they make a detailed documentation with ground penetration, rather also to see for the final structure, are there any negative karstic features, any cavities around the tunnel, which then probably later on can negatively influence the operation. And then in case they found something, of course, also outside the tunnel, they do some measures really to fill, for instance, these karstic cavities with concrete or whatever. So a very nice example here you see from this first step. Okay, there were some indications, probably there could be a cavity, and then after crossing this situation, they made this ground penetration radar, and they see, okay, 4 meters below the tunnel floor, there's a big cavity, which then, of course, was grouted. With investigation, of course, we collect a huge amount of data, and it's also highly important to have a proper data management. I give you now a final example of the Erzgebirge tunnel between Germany and the Czech Republic. Also huge tunnel, maximum overburden not so high, but will reach some 400 meters. It's this typical double tube system for high-speed trains in Europe. And it's the time design process and investigation process is ongoing, and we expect to start in around 3 to 5 years. What's interesting here is that you see from former times there are a lot of available data. So I said this Erzgebirge in German means ore mountain. So starting from the medieval age, there were a lot of mining work, and that's why there are a lot of drill holes, and still this information is existing around 2,900, almost 3,000 existing shallow drillings. All these were put into this data management system, were compiled in this system, and the colleagues there can really properly work in this system. They can do some modeling. They can show all the specific data. And they combine mapping with geophysical data, with drilling data. All is compiled in this three-dimensional model. So you can show or you can work out some specific images for complex situations. I will not go into detail, but anyway, at least to give you an image what is possible. So a proper data management provides, from my point of view, it's mandatory, and it provides various benefits. So you can combine data from different topics. You can comfortable zoom in and out. You can decide about the degree of detailization. You can overlay data. You can do some modulation and interpretation, which in particular also in the future will be highly supported with these developments in artificial intelligence, which will be really a task of the next decade. It's easy also for communication, so it provides you a lot of benefits, but also this idea must start at the very first beginning of a project and of a investigation program. So you could say to me, so just 2 or 3 minutes. Is everything okay? Yes, if everything okay. No, I come to my first slide. So we know a lot, but not everything. I give you only these 2 examples from the Lötschberg tunnel some 15 years ago. A long tunnel, a long base tunnel in Switzerland. So very nice, crossing the Western Alps. Let us have a look on this detail. It was expected to have these conditions, but there were some approaches that say, okay, probably a carboniferous syncline could also meet the tunnel alignment, but it was decided no, it will not happen at the same, sorry to say, shit happens. So at the end it happens. So you see the results, long-term deformations, more than 1 meter of deformations, problems in tunnel support and so on, with of course huge extension of construction time and costs. Also in the Coram tunnel we had problems, so we did really good investigation. So our idea was, so the overburden in this case is roughly 800 meters. We said from the mapping and from the drilling, okay, this fault zone will have this direction, but at the end it turned here and we met this fault zone here. So a huge we encountered with both TBMs this fault zone. We had overbreaks in this way. We did some drillings. We have collapse also for the second TBM. At the end, we had standstills of several weeks, and of course, a lot of further investments to keep the TBMs running. So what we have to consider, and again, okay, we have the responsibility and we have the tools. Here you see the results. Here you see how it could look if you have to evacuate the machine and which is clogged. So by having all this knowledge, having all these tools, there are still some situations which we have to consider that we cannot solve everything. So base tunnels and tunnels with higher overburden usually complicate the ground investigation. That's quite clear because of overburden and several other aspects. They increase the risks, but on the other hand, we have a big advantage. Normally, we have sufficient time and budget for a good ground investigation, in particular in case of these projects. A professional quality-driven engineering geological investigation requires a structured process, sufficient resources, and of course quality in planning and execution. That's quite clear. Geological site investigation requires a continuous self-improving process, which should be complete not earlier than at the end of the excavation. In the future, I'm quite sure we will have a lot of more benefits by using these techniques of building information modeling and artificial intelligent. Normally, we also know that investigation is not really cost effective. So all these projects, I know the content of investigation is in a range less than 1 to 3% of the entire project budget. So also from the economic point of view, that there is no reason why we should not carry out really proper investigation. But at the end, we know a lot, but also we have to recognize that there are limits, that we have our limits. But despite this recognition, we have to look for the best approach. This is our responsibility, and this remaining risk, okay, you have to be countered with a flexible contractual and organizational solution, at least then during construction. Thank you very much. Thank you for your attention. And at the end, the bill will be presented to us. Usually it is lower, it will be lower if we have done a proper ground investigation. Muchas gracias.